Alright, today we're going to start with section 4.2, which is graphing exponential decay functions. So this is going to be really similar to graphing exponential growth functions. There's just going to be a couple differences. So first of all, an exponential decay function it has the form y equals a times b to the x, just like the growth function, but this time a is greater than 0, and the base b is going to be between 0 and 1. So it's going to be a fraction that's less than 1. So you might see fractions that are greater than 1. Those are still exponential growth. We call the base b of an exponential decay function, that's called the decay factor. So this is the parent function for exponential decay functions. It always goes down, so it's always in this shape, whereas growth functions were always like this. So this was an exponential growth function, where it's getting bigger and decay is getting smaller. Notice that the x-axis is the asymptote for these exponential decay functions unless you move it up, which you're not going to see in examples like that today. So for the asymptote, it's always the x-axis, or you can just say y equals 0. That's your asymptote. Which means that your domain is all real numbers, because you can have all values of x, and your range is always going to be greater than 0. Y is greater than 0 because it's greater than your asymptote. So, for example 1, we're going to graph this exponential decay function. So it's easy to make a table. Please make sure you're graphing these nicely. I have a couple people who are graphing them quite incorrectly. Make sure you're graphing neatly. Put a couple points for me so I can see that you actually looked at the table. So if you go to your y equals, type 1/2. Make sure it's in parentheses, raised to the x, and then just hit second table. So the asymptote should be at the x-axis, so you're going to notice that it's going to get really close to 0, but it's never going to hit it. I'm going to start at -4. That's going to be too far for me to graph, but we'll just show it. 3, -2, -1, 0, 1, 2. We'll go down to 3. So at -4 it was at 16, which is too big for me to graph. That'd be off the graph. But -3 will be at 8. -2 it's at 4. -1 it's at 2. At 0 it's at 1. At 1 it's at 1/2. At 2 it's at 1/4. And then at 3 it's at 0.125. So if I graph this, oops, sorry. Let's see, this goes up to 1, 2, 3, 4, 5, 6, 7, 8. Oh, actually, this goes up to 16. And then it goes over to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this goes to 11, that goes to -11. So at -4, I'm at +16. At -3, I'm at +8. 2, 4, 6, 8. At -2, I'd be at 4. At -1, I'll be at 2. At 0, I'm at 1. At 1, I'm at 1/2. At 2, I'm at 1/4. And at 3, I'm really close to that x-axis. So when you graph this, make sure it doesn't actually cross the x-axis. Okay, it's just going to kind of run along it. So my domain, just like it said in the definition, it's going to be all real numbers for all of these. You can have any values of x. Remember, domain is any values of x. And it doesn't matter what value of x you get, you're going to find something, okay? That's your domain right there. For the range, that's the values of y's that are allowed. And if you notice here, y starts at 0 and goes up. So you can say y is greater than 0. It's not equal to 0 because our asymptote is at 0. So our asymptote is at y equals 0. And that's always going to determine your range where your asymptote is. And in this case, it's right here. Which dictates what your range is. So the worksheet is pretty straightforward because I believe it's going to be all the domains will be all real numbers. The range should all be where your asymptote is, and I think all the asymptotes are the same for the worksheet.